After 15 minutes, your power plant is getting new schedule. For power plant users, it's like a disruption in the way you operate plant. Corrosion is universal truth. You cannot avoid corrosion in totality.
So basically, you're looking at measurement, analysis, corrective action, control.
Yes. In that one restart, you lose something around 2 crores of Indian rupees.
Wow.
So it's a huge loss of productivity.
So water chemistry seems like a very critical element. Do you see the industry actually waking up to this fact? Hello everyone, and welcome to a fresh episode of the FM Energize podcast. When we talk about steam and condensate systems, the thermal parameters often get a lot of attention. But to discuss another equally important area, we have with us Aditya to discuss the area of impact of steam and condensate cycle chemistry on performance of plants.
Yeah.
Welcome, Aditya.
Yeah. Thank you.
So one of the first things I wanted to ask you is that water chemistry often gets not that much of an attention when we talk about plant performance parameters, but it is actually a very important area from the perspective of uptime, from the perspective of overall efficiency, unplanned shutdowns, things like that. Okay. So is it just the corrosion on boiler water tubes, or are we looking at other parameters also?
If you talk about water chemistry, I will first get into why that becomes slightly ignorant area. Okay. If you see any parameters, whether you take a temperature, pressure, or even parameters like vibration, they, whenever there are changing from normal values, you have some alarms, you have some set points, and you can take corrective action very quickly and you can restore them.
Right.
Water chemistry is one of the I would say challenges is today if there is a disturbance in water chemistry, you will not see effect immediately. Okay, there will be sometime weeks, sometime months, and sometime years to go before you actually see issues and effect of those disturbances in operational chemistry. And that can impact a multiple way. It can impact in terms of efficiencies. It can impact in terms of life of that equipment like boiler or turbine. Or third, it can have impact even from a safety perspective. So you can come across the situation that there is a sudden failure of some parts and you cannot find out root cause in last 2 weeks or 3 weeks. So there are no events in last 2 or 3 weeks which are actually supporting that kind of failure.
Because it's a very delayed effect.
Yeah, so it takes a lot of time to actually see effect. So cause and effect has a huge, gap sometime.
Right.
And also, that means whenever such kind of failure customer or user is facing, they need to do really good root cause analysis. So it's like a forensic study of failure parts of those high pressure parts. Then you will find actually root cause back somewhere where you are not operating system as per chemistry parameters recommended. You deviated somewhere, and then you see effect today. And that's why I would say one of the reason that water chemistry is slightly ignored when you come from an operation perspective, because their output or starting plant quickly, those are first priorities for users. Whereas when you talk about issues related with the water chemistry, it's not going to cause me any major issue tomorrow. So I can just ignore sometime those alarms and go ahead. But that impacts in the long term in terms of efficiency of that equipment, in terms of life of that equipment, and also sometimes there can be catastrophic failures of pressure parts, which can lead to accidents also.
Right.
Yeah. So
it plays a very critical role on safety aspect also.
Correct.
Yeah.
So that's why it's very, very important that this need to be monitored circuits very continuously, so that whenever you face any issues or challenges, you can look back for old data and actually come out with actual root cause of these failures, and you can avoid those in futures.
Right.
Yeah. So it's very, very important to have a proper monitoring of complete water cycle chemistry to actually maintain it on a required levels.
Understood. So we talked about different water chemistry parameters.
Correct.
Okay.
Yeah.
So can you give us a few examples of what potential problems or potential failures that you see if the water chemistry parameters are not correctly monitored? So you mentioned corrosion, for
Yeah.
example.
So if you see water chemistry related issues, you can bucket them into generally in broadly in two categories. Okay, one is issues related with the deposition,
Right.
and second issues related with the corrosion. Okay, issues related with the deposition is like deposition of scales in tubes, which will reduce thermal efficiency and heat transfer from one media to another media, and this kind of issues can also lead to some failures also. Like there is a under deposit corrosion, so there are
Right.
deposits, then below deposit there is a localized corrosion, and then it leads to failures.
Right.
Second issues apart from deposits is the corrosion related issues, where actually part of metals corrode. So there are different mechanisms. So it can be reaction with oxygen, dissolved oxygen in feed water, or oxygen which actually oxidize metal,
Right.
which leads to failure of because then locally it gets weakened, there are pitting, and then there is a failures. Or there can be stress corrosion cracking, so elements like chlorides, fluoride, sulfate can cause stress corrosion of high pressure parts.
Right.
And then there is something like a flow assist corrosion, where
Right.
actually because there is a water or steam is flowing through pipelines,
Right.
so it whatever corrosion products, it's actually scratching surfaces, and
Right.
it can lead to like a erosion. So there are different corrosion mechanism, but broadly, if I can say, these are problem related with the deposition, problem related with the corrosion, and both can be need to be tackled when you operate any high pressure steam and water cycle
Right.
or circuits. It can be power generation, where you actually generate steam, use it on a steam turbine, get it back as a condensate, put it back as a Rankine cycle. Or it can be even cogen plant or process plants, where steam is generated and utilized in plant, and then you recover that steam as a condensate and put it back into system. In both cases, you need to be very careful about overall purity and contamination locations, where there can be ingress of impurities in this cycle and can lead to failures related with the deposition or corrosion.
That's interesting, actually. And I also like the point that you mentioned with respect to both uptime and efficiency actually getting affected because of this. Okay. So I have heard about boiler tubes failing because of issues like corrosion, which actually shut down the plant for a considerable amount of time, which is a huge loss to the operators or to the customers. So is that the only instance, or do you see any other areas where both uptime and efficiency are affected?
Yeah, so I will talk first about, I would say, uptime. So, as you rightly mentioned, that any failure of these parts will put down the plant for a long shutdowns. Okay, so if you talk about boiler or steam generators, if you really see history of operations for any plants, you will see 40 to 50% of failures in boilers are because of water tube failures or tube failures.
Wow.
So tube failure is a biggest contributor of loss of uptime in boiler. Same way, if turbine is down, it is generally because of high vibration or any other issues. But if you again go back in a root cause, that is a deposition of impurities or salts on the surfaces of turbine blades, erosion of turbine blades, which lead to force outages or shutdowns in these plants.
Right. So
Okay.
even the depositions can lead to vibrations,
Yeah.
which are going to cause subsequent shutdowns.
Correct.
Yeah. So
So-
ultimately, it boils down to water chemistry again.
Correct. So, end of the day, if you go to root causes of any of the unplanned shutdowns or force outages, they will mostly point towards water chemistry,
Right.
and which is not yesterday or two day before yesterday's issues.
Right.
Those are long accumulated issues which suddenly force to such kind of outages. Now, if I talk about efficiency, so or everyone knows that deposition in boiler tubes will reduce heat transfer rates considerably reducing thermal efficiency of the
Correct.
boiler.
Correct.
But at the same time, such kind of deposits on steam turbine blades, okay, because steam turbine is very critically machined component where it is designed for high efficiency, where actually even slight change in a surface roughnesses of these parts of steam turbine can lead to reduction in efficiency. And you can imagine that a steam turbine which is generating 800 or 660 megawatt of power, and if there is a loss of even 1 or 2% efficiency, is a huge loss in terms of
Correct.
actual efficiency of the plant.
Actual delivered output.
Yeah. So to get a same delivered output, now you are burning more coal, more oil, more fuel.
Right.
So best way, if you can maintain purity of steam and water entire cycle, that will actually not only will help you to improve efficiency, but also will help you to unplanned shutdowns, which are huge cost. So you imagine if you go for a shutdown for 800 megawatt plants. So it's not just a small machine that you just start it with a keys, you know.
Right.
So you need to restart it. So considerable amount of fuel you will burn for restarting, and whole process you will lose huge man hours as well as huge time in terms of loss of productivity. So loss of productivity is actually biggest contributor when it's unplanned shutdowns.
Because even if we talk about a power boiler or a cogen boiler, they are huge equipments. Even the shutdown will take considerable amount of time just for the system to cool down.
Yeah, so number says that for 800 megawatt, if you go for any unplanned shutdown and you want to restart again, in that one restart you lose something around 2 crores of Indian rupees.
Wow.
So it's a huge loss of productivity. You keep aside actually cost of repairs, cost of equipment. Those are actually peanuts in front of loss of productivity and how many days you will lose in just restarting that plant.
So water chemistry seems like a very critical element. And do you see the industry actually waking up to this fact that they are actually monitoring the systems better? And if there are any gaps, where do you see those gaps coming out from the criticality perspective?
Yeah. So if I see overall industry scenario today, if you go to all large power plants, there are slightly awareness is better. I would say some of the users are actually not only going in a depth of these measurements, but also trying to find out root causes, try to take a corrective action in operations to restore and to maintain plant at highest efficiency and uptime. But as I mentioned, is steam as a utility is used not only for power generation, it also used in process. So there is a lot of awareness required in the process industry and users of water tube boilers, where still like cogen plants and captive power plants still need to go. There are a lot of improvement areas where I can see you can actually monitor this chemistry properly and take corrective actions automatically. Right now, most of the as I mentioned, for water chemistry, most of the actions are taken manually. Though monitoring is done automatically or through instruments, but still actions today are taken manually. And then because tomorrow nothing going to fail. So that's one of the reason. But down the line, over the years, you will lose efficiency as well as uptime for entire equipment. And sometimes some customers also faced catastrophic failures of these pressure parts leading to accidents, which is actually huge loss of even reputation for those companies. So if you see all these aspects, I think maintaining water chemistry is quite important aspects of operation which every user should be aware of and should get into depth of what need to be done in terms of corrective actions.
Understood. So in terms of water chemistry, I mean, we discussed corrosion, which is typically accounted for with the presence of oxygen. Okay. So do you think oxygen is always the culprit, or do you have any other aspects like particulates, or you have some silica content? So what are the different parameters that need to be monitored closely for water chemistry?
So as I mentioned before, that we have two kind of issue. One related with the depositions, one related with the corrosion. So what cause deposition? So first of all, the elements like hardness related causing salts, calcium, magnesium salts, and silica.
Right.
These are major reasons which can cause deposits on a boiler parts or as well as on a turbine. Uh, I would say most of water tube boiler, at least today, are using demineralized water. So DM plants actually take care of major issues related with, I would say, hardness causing salt or salt causing deposits. Though some elements like silica are very difficult to take it out from water because of their nature. Sometimes it goes as a colloidal form, sometimes it goes into reactive form. So that kind of treatments need to be enhanced uh, uh, for avoiding deposition related issues. But when you talk about corrosion related issues, those are mainly because of if you cannot maintain pH or oxygen levels in cycle. Okay,
Right.
so when water enters into boiler circuit, uh, once demineralized and DM plant, this demineralized water also need to have some actions need to be taken in terms of enhancing its pH on alkaline side. So we put some chemicals to enhance pH on alkaline side, and also you need to take care of dissolved oxygen, because any reaction between metal and oxygen is a corrosion.
Right.
Okay, is actually one of the areas. So most of the feed water treatment for boilers are actually segregated or categorized based on how you are going to handle oxygen and pH together. Okay, so there are different treatments which actually adopted for feed water of boilers.
Okay. And this will also depend on the metallurgy of the boiler components.
Yes,
Yes.
correct. Yeah, correct.
So,
So if you talk about boiler metallurgy, so in many circuits, I would not say only boiler metallurgy, it's a metallurgy of entire
entire
cycle,
plant. Yeah.
entire plant. So if you have mixed metallurgy,
Right.
for example, you have some iron and iron alloys, because it's a most of the pressure parts are made up of iron and iron alloys. But at the same time, if you have some copper, cupronickel used in heat exchangers or condensers or LP heaters,
Right.
then you have now two metals to handle.
Right.
Okay, from corrosion perspective. So you have iron and iron oxide, iron and iron alloys, which you want to avoid oxidation, and at the same time you have some copper, cupronickel, non-ferrous alloys where you want to avoid corrosion. Now, problem is that when you talk about such mixed metallurgy, we say, uh, you know, reaction of oxygen at different pH has a different rate of
Right.
corrosion. Okay, so in such mixed metallurgies, people are go for AVTR treatment, all volatile treatment with reducing agent. Okay, what this treatment does? So you need to remove dissolved oxygen in totality
Okay.
from feed water
Completely.
completely to make it as low as possible, ideally zero.
Yeah.
So you use mechanical deaerators to deaerate water. In addition to mechanical deaeration, we add reducing agent, which is we call the oxygen scavengers like
Right.
hydrazine, carbohydrazide, which reacts with oxygen and kills oxygen in totality. And then there will be a small residual of this oxygen scavengers which you can monitor. So by monitoring pH, dissolved oxygen, conductivity, and residual hydrazine, you need to control actually dosing of this oxygen scavenger and pH boosters in AVTR treatment. But at the same time, if you go for some circuits, which are all ferrous metallurgy, okay, so now modern power plants are coming with only iron and iron alloys. So they're going for alloys like P22 or P91, P92 for supercritical boilers. But their low pressure circuits or feed water circuit also includes carbon steel and iron alloys. So if whole circuit is with a single metal,
Right.
base metal, you
Right.
can iron or iron alloys. In that case, you can actually go for a better treatments also. So new treatments were adopted in such plants, which called AVTO treatment. This all volatile treatment oxiding environment, and OT treatment, which is the oxygenated treatment. Okay. In both these treatments, actually, what we do, we try to maintain pH in a particular range, and dissolve oxygen also in a particular range, which will form
Okay.
a very strong oxide protective layer on iron,
Right.
which will be very strong a layer of oxides, and which so oxygen will not penetrate through this layer to base metal and increase corrosion.
So you're actually monitoring oxygen instead of killing the oxygen completely. You're actually maintaining it at an optimum
Yeah.
level to ensure that such layers are formed.
Correct. So but to create such layers, you need to even maintain pH also in a certain
Right.
band. So pH will be maintained on alkaline side between say 9 to 9.8 or 8.5 to 9.5, in that range at various location, and dissolved oxygen is also maintained between say 80 to 120 ppb, in that range. So by maintaining these two, you can actually form oxide which is very strong oxide, which is protective layer. And there are some additional advantages also, because in such cases you are not dosing a third chemical in a
Yeah.
process like oxygen scavenger, which can have some other issues. At the same time, you can get a lesser pressure drops in steam water cycle,
Right.
and actually you can get a better results out of this. So these treatments are actually recommended internationally by IAPWS, VGB, EPRI. They are actually now working a lot on these areas where you can actually go for this treatment. So most of the large power plants already migrated from AVTR to AVTO or OT treatments, but still small power plants or captive power plants are on AVTR treatment because of mixed metallurgy in their
Right.
entire
Right. So
circuit.
because it will require some capex also in terms of changing the equipment with respect to
Yeah,
the mixed metallurgy
correct.
components.
Yeah.
Okay, understood. Okay, one other question I had, which is with respect to the changing load patterns. Okay, so we are
Okay.
seeing a lot of renewables come
Yeah.
into the mix in a big way, but they are unreliable. They are seasonal. Okay, with respect to day-night cycles as well as season-to-season cycles. So power plants tend to be base loads still, but their operations are no longer the steady-state operation they used to be maybe
Correct.
10, 15 years
Yeah.
ago. Right. So, are you seeing any operation-related challenges coming out of it, and how is it affecting the water chemistry side?
Yeah. So if you talk about particularly thermal power plants till date, okay, most of the thermal power plants were designed for a base load operation. Okay, so they were, today my power plant is designed for 500 megawatts. So people used to talk about PLF, plant load factor. So
Yeah.
my plant is operating on a 499 to 501, so it's on full load. So whenever you're talking about such a steady operation, everything is like in equilibrium.
Yeah.
Okay. Chemistry also will be in equilibrium. You will have very steady rates of dosing. Okay, there are very small disturbances in load patterns, so small changes in the levels of drum. So everything is quite constant. But as renewable is coming into grid worldwide, not only for India, operation patterns are going to change. Okay, so if you talk about today situation in India in 2025, today 50% install capacity is coming from renewable.
Wow.
Okay, in a grid.
That's quite
But
significant.
it's the install capacity.
Right.
But at the same time, if
Understood.
you talk about real generation, is around 38%.
Right.
So you have something which is a 50% can contribute to power grid, but now it's contributing only 38%. But you need to have a grid stability,
Yeah.
need to have a constant voltage and frequencies.
also, yeah.
So your now thermal power plant is has a job to absorb these fluctuations in a grid. Okay, so traditionally you were operating very steady load pattern, constant load. Now each after 15 minutes, your power plant is getting new schedule. So each within 15 minutes you need to
Every
go
15 minutes.
yeah, so for power plant users, it's actually very, you can imagine it's like a disruption in the
Right.
way you operate plant.
Correct.
When you talk about water chemistry also, now as there is a change in pattern of load, you need to adapt to that in terms of to maintain chemistry also, because you are deviating away from equilibrium to somewhere very dynamic situation. So when you talk about thermal power plants, you can categorize into three critical aspects. One is the startups, because earlier you used to start plant once in a year, twice in a year. Now you need to restart your plant maybe weekly once, or some plants even you know so quite more frequent startups. So ramp up you do,
Right.
and through when you ramp up this power generation, you need to go through various pressures. So lot of challenges in that area. Secondly, you will go for a cyclic operation. As I mentioned, each 15 minutes today, power plants are getting new power or load they need to generate and give it to grid. So that also has a lot of changes in flow or pressure, sliding pressures, which also lead to some issues related with the chemistry. And now you will see some of the plants which are not very efficient need to be put off when you don't need power. So you will
Right.
see more shutdowns. So even during shutdowns, you need to preserve boilers and entire cycle, because
Right.
standstill corrosion is also a new challenge.
I understood.
So all three regimes of operation will have a direct impact on corrosion rates, direct impact on depositions, flow assist corrosion. So
Right.
you need to monitor entire cycle now more rigorously, and you need to take some corrective action more real time also,
Right.
in terms of dosing rates, in terms of control of dissolved oxygen or pH. Now it's going to be more real time.
Yeah.
So a lot of opportunity there for aspects like monitoring of
Right.
these equipments.
Understood.
Yeah.
So I get where you're coming from. So if it is running in an equilibrium, then
Yeah.
almost everything is going there. You monitor specific KPIs. If they're deviating, then you take the corrective action.
Yeah.
But with everything changing with a frequency as
Yeah.
strong as every 15 minutes, okay, under that condition, all of this becomes very much active, very much
Correct.
proactive.
Yeah.
Okay, so the real-time monitoring becomes a very, very important parameter in that case. So I get your point on this. So my question to you to follow up on this is that would you have any specific recommendations to people who are operating such plants in terms of what they should look out for in a way?
So from steam and water cycle chemistry perspective, there are a lot of parameters are monitored today. So you have a pH, you have various type of conductivities, dissolved oxygen, silica, sodium. So those parameters are required as it is. But those need to be monitored, and somewhere they need to be linked back to controls.
Right,
Okay. So
right.
that is going to happen, and that is required to be looked at how you can get a robust measurements and how you can utilize them for controls of these chemistry parameters.
So basically, you're looking at measurement, analysis,
Yeah.
then corrective action, and control.
Yes.
Hopefully, we'll see with the rise of AI, maybe we'll see an automated version of this entire
Correct.
cycle also.
Yeah. So that also AI going to contribute a lot, because as I mentioned, now you have data for years, and now you can
Right.
actually go for a real root cause of issues with that data. So that also going to contribute. But at the same time, you may need to have some additional parameters you can monitor. So they are getting more and more popular, like dissolved hydrogen or turbidity.
Right.
These are getting more popular because of higher corrosion rates, because corrosion is universal truth. You cannot avoid corrosion in totality.
Right.
So because of this operation regime change, you will see higher corrosion rates. So people are going for some additional measurement to find corrosion products, like using turbidity and other measurements. So there are a lot of other measurements also coming in a picture, which earlier were not so critical because you were working on a steady state. But at the same time, now I would say you will see more real-time importance of these measurements, because I remember earlier plant is operating on a few hundred megawatt steady load. Even everything is steady. pH is also steady. Dissolved oxygen is maintained. But as you will deviate from it, you will see disturbances in even these parameters. to restore condition, you have very less time. So you need to actually go for some good technology for adapting these measurements and use them in a daily life.
Right.
So you will see change in operation, the way people are operating plants also.
That's actually right, because if at an equipment level, the more the more carefully you actually maintain the equipment, the better uptime, the better efficiencies, all of that you'll get. And you have given an in-depth analysis of what all different parameters are responsible for it, or what should be the corrective actions, and so on and so forth. So thank you very much. Any last thoughts for our viewers in terms of what they can do in terms of improving performance at their specific plants?
So I would say today water chemistry, till date was like slightly ignorant area. You have something which is going in parallel. So you're operating plant your way. There are some alarms and set points you are taking care, but chemistry is going in its own way.
Right.
Because it's done manually. Sometimes you have only some deviations you need to take care. But now even integration of water chemistry measurements into daily operation is going to be very, very critical for all users. Wherever you are using steam and water as a utility, everywhere you will see more and more importance to these type of issues and monitoring. So just see how you can have a robust, reliable measurement in place so that you can actually go for controls and future corrective actions as you go along.
Right. So even the awareness needs to be improved in that
Correct.
context,
Yeah.
in a way.
So as I mentioned, in large power plants, awareness is good, but still small power users, small captive boiler users, they were not bothered about these kind of issues much.
Right.
But this kind of issues can lead to permanent loss of efficiency, unplanned outages, and also sometimes some catastrophic failure of pressure parts, which can be avoided, and we can change scenario in industry by
Yeah.
proper
So
monitoring.
in terms of not only performance and uptime, but also from the perspective of safety,
Yes.
water chemistry becomes a very, very critical element. And it's good to see that it is becoming more and more mainstream,
Correct.
that awareness is increasing, but there is still some distance to go.
Yeah, sure. Yeah.
So thank you, Aditya, for your time. Just to summarize this for our audience, we talked in depth with respect to there is a certain amount of awareness gap with respect to water chemistry parameters going into steam and condensate loop systems. The awareness is improving, but there is still a considerable amount to go. We need to be aware of different water chemistry parameters that are important to measure, such as pH, such as conductivity, such as dissolved oxygen, such as turbidity, and each of them will have a different impact on the system performance. So unlike the olden days, today the water chemistry parameters are dynamic in accordance with the dynamic nature of the plant operation itself. And as a result, it becomes that much more important for the users, the operators of these particular plants, to ensure that these parameters are carefully monitored, that any deviation in their performance are captured, insights derived from that, and those insights are then communicated for effective corrective action, which will ensure not only a good efficiency as well as a good uptime, but it will be critical from the perspective of safety for steam and condensate loops like this in different plants. Additionally, going forward, we see a lot of digital technologies coming into the picture, and as a result, collecting all of this data, because historical data is considerably voluminous in terms of its availability. So collecting all of this data and feeding it to a digital technology tool can give us better parameters, but only if the water chemistry channel is aligned with the other KPI channels of a particular plant. So from that perspective, it is very, very important for people, for operators, for engineers, for supervisors and plant heads also to be very aware of what different chemistry parameters they need to look out for. So the awareness part is very, very important, and we we recommend that you find more information about this, you learn more about this, educate yourself. If you need any help from us, please reach out to us and subscribe to the Forbes Marshall YouTube channel for content similar to this, and look out for the FM Energize podcast upcoming episodes. Thank you.